Okay, and lastly, we were gifted with a pretty easy momentum question. So at time t equals 0, block A slides along a horizontal surface. The masses are given. The blocks collide elastically. And as a result, the magnitude of the kinetic energy change of block B is 9 joules. All frictional forces are negligible. Determine the speed of block B immediately after the collision. Well, typically we'd say do some momentum stuff here, but we actually know 0 initial velocities here. So that's actually not very helpful, because to do after the collision stuff, you need info about before the collision, and we don't. We just know block A is moving, block B is not. But what we do know is that delta K on block B is equal to 9 joules. And I know it's positive because it stopped. So this means that 1/2 mVb final squared minus 1/2 mVb initial squared equals 9 joules. But also, we're told that block B is initially at rest, so that term is 0. So now we can just do some computing here. So the mass of block B from the figure is just 2 kilograms. And that's it. So unsurprisingly, we do get a perfect square here, which is always a good sign. So the square of block B is 9. So that means the velocity final of block B is just 3 meters per second. And I know it's positive due to momentum. Okay, and now we have a graph. The graph shown in figure 2 represents the positions of block X, of block A, block B, and the center of mass. So, before I even do the rest, I know the center of mass is going to be constant because that's what it means for momentum to be conserved. So VCM has to be a constant during all collisions, unless if there are external forces. So I can just go here and I can just continue the line. And you are my X of the center of mass. Then we'll use our before and after the collision situation to get B. So block B, initially not moving, but then after the collision, we said moving at 3 meters per second. So I'm going to start here. And if it's moving at 3 meters per second, well, that means that after 1 second, I go 3 meters. So up 3 over 1. So that's B. And now we got to figure out A, which is when we can use momentum conservation here. So now we can use the fact that the momentum before has to be the momentum after. So the mass of block A times V of block A is the only thing that's moving before. And that's equal to the mass of B times velocity of B plus the mass of A, velocity of A after. So block A is 6 kilograms. We don't know how fast it was moving. Sorry, we do. We actually can figure that out. We have the graph. And then I'll just set up everything else. Velocity of B. So B was 2. Its velocity was 3. We're solving for this VA. So actually, we can figure out the velocity of block A before the collision. We have a graph. But sorry, that's what happens when I'm doing these live. So, in 1 second, block A travels 2 meters. So this is 2 meters per second here. So then we can solve it, and we get 12 is equal to 6 plus 6 VA. So we get 6 is equal to 6 VA, or VA is equal to 1 meter per second after the collision. So that means we got to change our velocity over here. So after the collision, it's going to go up 1 over 1. So there's our A. And you can check that this elastic collision works too, just by computing the K's before and after. So this is definitely correct here. So there's A, there's B, and then there's the center of mass. Consider in the original scenario, instead of colliding elastically, they perfectly inelastically collide. Describe how the center of mass line changes. Well, based on our principles here, delta V of the center of mass as a function of time is equal to the net force acting on the system. So this does not change whether we're colliding elastically or inelastically. So since the sum of the external forces acting on the system is 0 in each case, delta VCM equals 0 each time. So this means line is unchanged. And interestingly enough, if they did collide inelastically or perfectly inelastically, their shared velocity would be the center of mass velocity. And you could compute that. You could compute that their shared velocity after the collision is going to be just the momentum of A divided by the total mass. Yeah, pretty standard. This was a good question. I like this. Oh yeah, point breakdown. Let's see. 7 points again. 2. Got a point for this, point for algebra. 2 points for this. And then probably 3 points for each of these. So a point for not changing the center of mass line, a point for making the B line what it should be, given your part A answer, and then doing momentum conservation to get block A's velocity. So this might even be 4, and this could even be 1 point maybe. Solving the momentum. This is quite a point here, if that's only one of them. So I might change that. I might think that this is 1 point. I think that might just be 1 point, and this instead might be 4. And then for marking my points here, point, 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 point. Probably something like that. Yeah, this was quite an interesting question. Very unique.